Let's go on part number 2. All right, I apologize for the abrupt ending of part number 1. I overran my time limit on how long these videos can be in order to save them, so I had to go back and trim a little bit out. So right at the end there, we were talking about the idea of orbiting astronauts orbiting the Earth, all right, and the whole idea that turns out they're in free fall. So we have the Earth, and if we were to throw something, because of forward inertia, it goes straight. Gravity pulls it down and makes that curved path. Well, if they're going fast enough, all right, they're going fast enough, then they make that curve, and the curve comes out around the outside of the Earth. Well, that curve continues. It goes to here, and then it continues and goes to here, and then it continues and goes to there. And notice it never runs into the Earth that's in the center. And it just keeps going around and around and around and around and around. And actually, those astronauts then are actually just falling around the Earth. All right. So they're in a free fall. They're like going on a power tower at Cedar Point, or any kind of like roller coaster at Cedar Point. Sorry, I had to think for a moment there. And they're like going for like 2 weeks, right? Or even a year inside of the space station, right? Now, why don't they like feel the way we feel when we're riding on power tower or a roller coaster? It's all because the idea that their internal organs actually get used to that sensation, so they don't actually notice it for very long. So, all right, so that's why astronauts they are weightless, because they're actually in free fall the entire time while they are, and the key word is orbiting the Earth. While they're orbiting, they're weightless because they're falling the whole time. And it all goes with those two scenarios up there. That it's because they have forward inertia and gravity. If they didn't have forward inertia, if they weren't moving forward, then they would just go straight down and end up hitting the Earth. All right. Okay, so that takes us then to question number. We're on question number 13 then. All right, so 13. Let me get over to that page. And that is give an example of Newton's third law. Well, Newton's third law is the idea of action and reaction forces. All right, so in other words, for every action, there is a reaction. And an example of that is I'm on a rolling chair right now. All right, if I were to take a bowling ball and throw it that way, all right, in order for me to throw it that way, I'm going to go like this, and I'm going to go backwards. Why do I go backwards? Well, in order to push the ball that way, I've got to have a force that goes that way, but at the same time, there's a force that pushes in the other direction. And that's the idea of an action-reaction force. The other thing that is another example of that is if you go hunting and you shoot a shotgun, right, and you put the shotgun right here on your shoulder. Okay? When you shoot the shotgun, in order for that bullet to go out that way, right, there's a force of equal force that comes back this way and hits your shoulder. And boom, hits your shoulder. Call it the kick of the gun. Right? That's the action and reaction force. Right? A rocket that takes off and goes up into space. We have the action force, the rocket going this way, but at the same time, there's the reaction force of the force going down of the propellant. Right? The rocket fuel blowing out the bottom of the rocket, that actually exerts a reaction force this way to give us the action force that causes it to go up. Right? So that's the idea of action-reaction forces. Right? Number 14, why is an action-reaction force not a balance force? So on this one, it says think about a gun and a tug of war. So on the idea of the gun, I shoot the gun, there's an equal force going that way as there is going this way. Well, that then seems like it should be a balanced force because there's equal forces going this direction. And if we had a tug of war, in the last chapter we talked about a tug of war where we have an equal force in both directions, then it's a balanced force and there's no winner on the tug of war. Right? Now the key thing is, what is this team over here, what are they exerting their force on? The rope. What's this team over here, what are they exerting their force on? The rope. So they're both exerting a force on exactly the same thing, the rope. Right? Now, what about a gun? If I shoot the gun, right, for the bullet to go out that way, right, it's exerting a force on the bullet. So it's going on the bullet going that way. The reaction force is on the gun going this way. So that's two different objects. It's not like the rope where they're both on the rope. This time you get one force on the bullet, one force on the gun. So it's on separate objects. So that's why we consider that to be an action-reaction force versus a balanced force. And that's what ends up causing the bullet to go out of the gun. Okay. Number 15. Describe how mass and velocity affect momentum. Right? Momentum, which is very similar to inertia that we talked about in the last chapter. The only difference is that every object that's out there has inertia, whether it's moving or whether it's sitting still. They all have inertia. Right? In other words, that's that resistance to change. If the object is moving, it's going to keep moving. Right? If the object is sitting still, it's going to stay sitting still. That's the idea of inertia. Now, what's momentum? Think inertia, but only moving. Right? If the object is sitting still, it has no momentum. But if the object is moving towards you, then it has momentum. Right? So a high mass, a big elephant, has lots of momentum. It's going to be really hard to get him to stop moving. Right? Low mass is very, very low momentum. It doesn't take very much to try and stop a ping pong ball that's coming at you. Right? So big mass, lots of momentum. Low mass, low momentum. And that's talking about if they're both traveling exactly the same speed. Now, what about velocity, which is, remember, kind of like speed, but we have to add the idea of direction. They're both traveling this way. Right? So let's take something really, really small. We take a ping pong ball. Right? If that ping pong ball is going really, really, really fast, it's going to have lots of momentum. You're going to have a hard time trying to stop it. That's like a bullet. Right? Bullets are very, very, very small. They have very, very little mass, but they have lots of momentum because they're going so fast. Now, if we take that same object, well, again, we'll take a bullet and you just toss it. Right? I just toss it. It's no big deal to stop it because it's not going really, really fast. It doesn't have high velocity, so it doesn't have much momentum. Right? So high velocity, high momentum. High mass, high momentum. Right? All right, last question before we go to the ones that would be in the book if we had the book, but I gave you the copy to do. 16, state the law of conservation of momentum. The law of conservation of momentum is that the total amount of momentum in a group of objects does not change unless an outside force acts on it. Right? So this idea is, think of the idea of playing pool. So you go to the pool hall and you're like trying to put the 8 ball in the corner pocket with the white cue ball. Okay. So what you want to do is you want to take that white ball, hit the 8 ball, and get all of the momentum of the moving cue ball, the white ball, to get transferred into the 8 ball to go and bounce it into the corner pocket. Right? And that's what we're going to end up with is transfer momentum. All right? Once I transfer it, then the 8 ball is going to take off going. Right? Now, will the 8 ball go forever? No, it's going to stop at some point. Now, what's affecting the 8 ball to make it slow down? Well, friction. There is friction present, so that's what makes it slow down, right? And that's why objects don't go forever. There was Newton's cradle that sits there and it like goes back and forth, and it comes down and hits the balls, and the ball on this side comes out, hit, the balls go, right? And they do this. Well, some people say, well, don't those things go forever? No, they don't go forever because there's friction. And because there's friction, we actually do lose energy. And because we lose energy, it's not going to go forever. Right? It is actually finally going to stop. Now, if we can ever get it so that there's no friction in something, then that type of machine will go forever and never, ever, ever stop. That would be amazing. Right? You ever come up with a way to do that? Call me, because we'll be rich. Right? So, all right. Well, now we go to the part that's in the book, or was in the book, looks like that, right? And we gotta go through those questions. So the first one, it says the net force acting on a moving object causes the object to do what? So if you exert a net force, a greater force than what's holding it, then the object's going to it's going to accelerate. It's gonna all of a sudden take off in the opposite direction, like the idea of kicking a ball, okay? You exert enough of net force on that ball to overcome the friction that's holding it where it's at and the inertia where it's at, it's also going to take off and go flying. Number 2, blank is the effect of gravity on an object. What is that? That's D, weight. How do we measure weight? That's really a measurement of gravity pulling down on that object. Number 3, which of these opposes acceleration due to gravity? Well, when I'm falling out of an airplane going skydiving, What's pushing up against me? Air, right? And that's air resistance. Air resistance is the force that opposes acceleration due to gravity, causing me to fall, right? Number 4, according to Newton's second law, Planck equals mass times acceleration. Well, force equals mass times acceleration. So the right answer is C, force. Force equals mass times acceleration. Number 5, what force causes a leaf to fall more slowly than a penny? Oh, remember that leaf, like in the fall, all of a sudden goes like this, goes down to the ground? Well, what's making it so it does that? If you drop a penny, it goes straight to the ground. Well, that leaf all of a sudden catches air resistance and reaches terminal velocity. That's as fast as it's going to go, because the air resistance pushing up equals the mass coming down, and it stops accelerating. Number 6, which illustrates Newton's third law? Of those ones, it's rocket propulsion, which we talked about a minute ago. In order to make the rocket go up, that's the action. We need a reaction, the jet propellant going out the other end. So there's the force on the gases coming out the bottom going, and that causes the other force on the rocket to cause it to go up. All right. I'm just about done with my time on this one. We're going to go to part number 3, so I'll see you in part number 3 in a minute.